Okay, that's 5 past, so I'm going to uh, get started now. So welcome to this, the latest Archer 2 webinar, virtual tutorial, whatever we want to call it. In this one, we're going to be looking at the new GPU development platform that's recently been added to Archer 2. There's going to be 2 presentations, a short one first by myself on behalf of the Archer 2 CSE team, who've been doing some testing of the development platform setup, and then a second presentation from the HPE Centre of Excellence, which will go into a bit more detail around compilation and architecture and things like that around the new GPU development platform. The idea is the presentations won't be too long, and we'll leave plenty of time, hopefully, for questions at the end if people want to ask things about the GPU platform. So let's just get started. So what I'm going to cover in this short presentation on behalf of the CSE team is a quick overview of the platform itself, what it looks like, though. HPE are going to dive in a bit more detail in terms of the architecture, the node architecture, and those sort of things. I'm going to particularly cover the scheduler configuration, how it's set up, and how you access the GPU nodes that have been added to Archer 2. We've got some example job submission scripts just to give you an idea of how it all works. Finally, I'm going to mention the GPU ECSE call that's open and have a look at what we're going to carry on to do in the future. What I would say is this hardware hasn't been on Archer 2 for very long, so we've only had a short amount of time to do the setup and testing. So everything here is a bit work in progress. You know, we've put up some documentation and we're going to cover some material here, but expect that to be added to and improved over time as we learn more and more about the new hardware that's available here. So it is by no means an exhaustive set of documentation, experience, and all those sorts of things right at this minute. But as time goes on, we'll add to it. So there's the obligatory partners slide. So the overview. Sorry, there seems to be a bit of an overlap of the text here and the conversion into the format on the online platform. The first thing to realize is it's a very small resource, right? There are only 4 nodes with GPUs, and each of those nodes has 4 GPUs. So there's only 16 GPU in total, and we'll get to the architecture in a minute. But these are not quite the same as some of the GPU nodes you might have seen in some of the large exascale systems in the US, where each of the GPUs is really 2 GPUs called the GCD. That's what the AMD GPUs look like, for example, on Frontier or even on Lumi over in Finland, if you've used that system. These ones are the PCIe cards, so they're half the size of the ones in these exascale systems. So that means there really are only 4 GPUs per node, not 8 as it is on the exascale systems. It's really designed for development and testing, not for use for production research. It's simply not large enough for the size of community on Archer 2 to be able to use for production researchers to gain experience of compilation, debugging and profiling, and use of these AMD GPU devices. It's fully integrated into the Archer 2 system. There's no separate login nodes for the GPU system, so you just use the Archer 2 login nodes. All the software for compiling for GPUs is available there, and it's all integrated into the scheduler as well. So that makes it pretty straightforward to get on and start trying to do stuff. It uses the same file systems as well as the Archer 2. So the way you use normal compute nodes, you should expect exactly the same file systems available on the GPU compute nodes, namely the work, Lustre file systems, and the solid-state NVMe file system as well. It's available to all Archer 2 users who have a positive CU budget, so you don't need to request any special access or anything like that. Anybody can submit jobs to the GPU as long as you have a positive budget, and there's no charge for the GPU node use. We've got documentation in the usual Archer 2 user guide. There's now a section on the GPU development platform in the user guide. And as I mentioned earlier, this is going to be added to and updated as we go on and learn more about the technology itself. I've got a very basic overview of the hardware. HPE are going to dive into more detail of this in their presentation. Essentially, each node has one AMD CPU with 32 cores. It's a Milan CPU for those who are interested. It has 4 AMD Instinct MI210 GPUs. So these are the half-size ones compared to the 250Xs that were in systems like Lumi and Frontier. And it's got 2, like the normal ARCHER2 compute nodes, it's got 2 slingshot interconnect. And there's some sort of node diagram here. It does have GPU to GPU direct communications between the GPUs on a node, and the MPI on ARCHER2 does support GPU direct, GPU aware MPI if you're going across nodes. And I mentioned the file systems earlier. It's the usual file systems available on these nodes. In terms of compiling, again, HPE are going to say more about the different compiling models, or you can look at the documentation, which has got more information there. The program environment GPU support is currently available on the login nodes. On the GPU compute nodes, you can get terminal access to them via Slurm. I've got an example of that later on. If you need, for example, to actually have access to the GPU for the compile steps, some build procedures actually need the GPU to be able to do auto detection and things like that. So you can get terminal on the compute node to do compilation. And it's on the serial data analysis nodes, accessible via the serial QoS2. The full details of the offload methods, instructions, examples in the HPE presentation that's coming up in a minute, and also in the documentation. In terms of the scheduler, you submit from the ARCHER2 login nodes as for any other job type on the system. Use your job script to just select the number of GPU you require. So you don't specify the number of CPU processors you want, or the amount of memory you want, or anything like that. You simply request number of GPUs, and if you're doing multi-node GPUs, the number of nodes you want as well. And that's the minus GPUs equals n option to Slurm. You're given an amount of CPU cores and an amount of memory commensurate with the amount of GPU requests, because these nodes can be shared between multiple users, because we want to give as many people access as possible. So if you request 1 GPU, then you'll get 8 CPU cores and 128 gigabytes of the memory. So that's a quarter of the memory and a quarter of the CPU cores. If you get exclusive access, you get obviously all the GPUs and all the cores and all the memory on a node. Once you've got your allocated resources, you then use S1 to specify how many tasks, MPI processing tasks in Slurm speak, which is MPI processes usually, and threads you want and in what configuration. If you try to request specific numbers of CPU processes, tasks, and threads and those sorts of things in your job submission script and the SBatch options, then you'll get an error telling you not to do that and to only pick the number of GPUs. Okay. And you'll see this in a moment in the example job submission scripts. As I said right at the start, this is really a test and development system, not for production research. I'll talk about the limits first. For all the QoSs on the GPU nodes, users can have any one user can submit a maximum of 2 jobs, one of which may be running per user. There's 1 hour maximum wall time, and there are some limits on the resources. For shared access, you could ask for a maximum of 2 GPUs, and for exclusive access, a maximum of 2 nodes, which is 8 GPUs in total. There are 2 QoSs, one for shared node access, access a GPU while sharing the node with the users. So you typically ask for 1 or 2 GPUs on single node, and it's got the highest priority of the GPU QoSs. If you want exclusive access, you get all 4 GPUs on a single node or 8 GPUs across 2 nodes. It's slightly lower priority to try and give fair access to as many people as possible on this resource. These are just our starting configuration. Obviously, we'll be monitoring the situation, monitoring how access is being shared out among different people across the system, and we may modify these limits if they're not proving useful, or if some other configuration would be useful for people. There may be times when access to the GPU nodes is reserved for training courses and things like that as well. So just be aware of those things. It's a small resource, and we're trying to give as many people a chance to access the nodes as possible. So here's an example job submission script for a single GPU, potentially on a node shared with other users, for 20 minutes. So in this case, you get the use case here, we're looking at one CPU process, so potentially one process, 8 CPU threads, and one GPU. So as I said, in the SBatch options, you only ask for the number of GPUs you want. And then once you have your GPUs, you can do whatever you want with them. We recommend actually use the start of before you actually run your executable. You can use the ROCM SMI command just to check what GPUs you have access to and what they look like. It's useful to check that you're getting the resources you think you're getting. And in this case, once you've got your resource, your GPUs, you can split srun within the job script to divide it up however you want and use it however you want. Potentially a slightly more interesting one. So this is the exclusive node access. Say I wanted 8 GPUs across 2 nodes for 20 minutes. So here my use case is 1 MPI process per GPU, 8 CPU threads per MPI process, and 8 GPUs. So we do something slightly different in our SBatch. We ask for the number of GPUs, 8, I think. Oh, I need to check that against things. I was maybe expecting that before. I'll have to double check that in the one in the documentation will be definitely right. I'll double check that this presentation one is correct as well and update the presentation if I need to. 2 notes. If there's anybody else from the CSE team who wants to chip in the chat to say whether this GPU should be 8 or 4 here, I can't remember if it's GPUs per node or GPUs in total.
I think it should be 8.
You think it should be 8? Thanks, Michael. Okay, yeah, so it's the total number of GPUs you want split across 2 nodes. So I am right. Here we do use the ROCM SMI command again. What we actually do is loop over the nodes in the job and run ROCM SMI on each of the nodes in turn to check we've got the right sets of GPUs we expect on each node. And then we also use XT-high to make sure we've got the right process, to check that we're doing the right sort of process thread pinning that we expect. And here you just use exactly the same srun options you use for your executable, and it will print out what the process and thread pinning looks like. There's a wider range of example job submission scripts available in the documentation that cover slightly more variations than I've got time to go into in this presentation. You can also get interactive jobs, use salloc to reserve the resources, number of GPUs, that sort of thing, and then srun to launch, just like you would for a batch job submission script. And there's a slightly different syntax. If you want to get a terminal on a GPU node for compiling, you can use srun and specify a terminal. There's an example in the documentation of how to do that. Once you've done that, you can't actually use srun again once you've got the terminal on the on the compute node to launch a parallel job. You need to exit out and then use either this salloc process or use a batch script to do that. But if you're just using a serial process for compiling or something like that, then you can get a terminal on a compute node. Look in the documentation for how to do that. While I'm here, I also want to mention that there's currently a call open in ECSE specific for GPU development. And we're expected to run 3 calls this year. The first call is open. And they're open to proposal support research across all of UKRI remit. Previously, ECSE has either been available for NERC or EPSRC work, and that restriction doesn't apply to this call. And give you up to 36 person months of effort available for call, a maximum duration of 2 years, and you can spend there's flexible ways to spend the effort. The deadline for the current ECSE call, for the currently open ECSE call, is the 19th of March to get your applications in for software developer efforts to enable for GPU related software development work. There's a link there on the ARCHER2 website with more information on the call. If you have any questions on the call, please drop us a line at the service desk. We're happy to answer them, or even to arrange a call with you to discuss further. So where are we up to so far? Oh, thank you, Claire. There's also a webinar about the call on the 8th of February. So where are we now and where we got to? Well, I've sort of given you a summary of where we are. We've been testing different compilation processes. HPE are going to talk about that, a bit more about that in a moment, and checking that things work so it's ready to go for users. In the future, we're going to look a bit more at porting software packages. Some work's already been done there, porting machine learning frameworks, potentially making them available. We're going to continue to investigate and document the functionality to improve the documentation. This will include things like performance libraries, debugging and profiling covered in more detail, and things like that. And then move on to some performance investigations as well. So it's a very quick overview of what the GPU service, GPU development platform looks like, and how you access it, the usual ways via Slurm, and by just logging into the login nodes for the development environment. It's available to all ARCHER2 users, and it should be available from around 4 o'clock this afternoon. So straight after this, or pretty much straight after this session, you should be able to log in and start being able to access the GPU nodes. There's 4 of them: shared node access, there's exclusive node access as well if you want, documentation and guidance are work in progress and going to be expanded, and there's the ECSE call. And there's the link again to the GPU documentation as it is at the moment. If you have any questions about the GPU development platform, well, we've got a chance hopefully to we'll have a chance today to answer any questions online. But if you think of anything else, you can just contact us at the service desk in the usual way, and we'll do our best to help as always, via email. I can even arrange callbacks to discuss things in more details, do screen sharing and all those sorts of things. So I'm going to stop now. Before we go on for questions, I'm going to hand over to Harvey Richardson from the HPE Centre of Excellence, who's going to do some more detailed technical presentation about how to use the GPU system. So I'm going to stop sharing, Harvey, so you can share your screen. Aha, here we go.
Okay, is everyone seeing the slides?
I can see them and I can hear you fine, Harvey.
Yeah.
Okay, great. So I'm Harvey Richardson. I work in the Centre of Excellence for ARCHER2. So there's a team of us, and I do the short straw to give this presentation, but I'm going to give the bulk of it, and then Douglas Shanks, also from the COE, is going to give the remainder at the end. So the agenda for the talk is the 2 pieces have already been done by Andy, and I'm going to look in a little bit more detail about the platform hardware, and then talk about the programming environment that's available, what programming models are available to program these GPUs, talk about the ROCm stack, which stacks are available, which modules you have to load to use these GPUs, which compilers are available. Then some little topics at the end about if you want to think about absolute performance and where your job is running, this GPU-aware MPI communication that Andy mentioned, to mention which profiling capabilities are available. And we've got a few slides at the end where we'll mention a bit about the experiences that Douglas had in just trying a few applications on the system. So just a second, I've got something on top of my slides which are annoying me. I've just moved it out of the way. So the GPU platform, in hardware terms, it's racked in air-cooled racks, so a little bit different from the main ARCHER2 configuration. And it comprises Apollo 6500 chassis, and each of those chassis has 2 nodes in. And those 2 nodes support a configuration which is one AMD EPYC 7543 processor, so that's a Milan processor running at 2.8 gigahertz, 512 gigabytes of RAM. There are 4 AMD Instinct MI210 PCIe type GPUs. So as Andy said, slightly different from the architecture you'd see in some of the larger systems around Europe, in that these are mounted on PCIe slots. 2 network interfaces connected to slingshot switches in the same way that we have on the nodes on ARCHER2 for the CPU side. And there are also some storage devices, although we haven't really decided how to expose them and how we would use them if we decide to do that at some point. The node, if we want to explode the node in more detail, so AMD have moved to this architecture that is based on having chiplets and then adding them together to build up what comprises something in the larger socket. So in this case, at the lowest level, the organization is slightly different from we have on ARCHER2. So we have 4 cores together, 4 Zen 3 cores in what's called a compute complex, and they share cache infrastructure. And in particular, they share a 32 megabyte L3 cache. And there are 8 of those in the whole CPU package surrounding an IO die. So essentially it's divided into 4 quadrants, and that's the NUMA layout of the node. So you have 4 NUMA domains and a 32 core CPU. So less cores than you have on ARCHER2, little higher amount of L3 cache per core, 2 network interfaces. So slightly different, but we don't really need the CPU power because we're really using this to host the GPU. So quite a large amount of 250 megabytes of L3 cache in total. Similar to the CPU nodes on ARCHER2, we have 8 channels of DDR memory. So that's the basic configurations of the CPU. The individual GPUs themselves are AMD Instinct MI210. So here's the pictures of what they look like. So these are dual slot width PCIe cards that fit into a PCIe 4 16 lane slot. And this is the new compute DNA architecture from AMD. The specifications are that you have at the highest level, you have 104 compute units, or if you want to think of individual threads, you have over 6,000 of those. And this clocks at 1700 megahertz, and its peak performance is 191 teraflops. And depending which metric you want to use, they quote different performances here. GPU memory is 64 gigabytes of HBM2E, ECC protected, and its peak memory bandwidth is 1.6 terabytes per second. So this is one of the advantages of GPUs, is this high memory bandwidth. And then, as Andy showed, the explosion of the node architecture, you have the EPYC CPU at the top, connected to both the network interfaces and the GPUs through PCIe lanes. I realize it's a bit complicated. Technically, there are switches in the way, but you can just think of this as one part of that CPU connects directly through PCI to an individual GPU. And there's a set of PCIe lanes, or single PCIe lane, if you want to think of it that way, connecting you to a single GPU. And then the extra interesting thing about this node is, as well as the PCIe connections, there's actually a daughter card that sits across the top of the GPUs that provides an Infinity Fabric interconnect or XGMI interconnect between the GPUs. So the peak performance of that is that from the perspective of one GPU, you have 300 gigabyte per second links to the other GPUs. That's the not to exceed number. And we have done tests of CPU to GPU bandwidth and GPU to GPU bandwidth, so we know those links are there. You can tell that from various commands. So that's the basic node architecture that we're targeting. And as Andy said, there's this nice command ROCm SMI, which you can run once you've got a GPU allocation, and it tells you a little bit about the GPUs that are accessible to you. So if you've allocated 4 of them on a node, you'll see output like this. So you see there's GPUs enumerated 0 to 3. The maximum clock here is 1600 megahertz. And if you ran this when you were actually running something, some of these values would be different. And it's useful. This is a very useful check to run, because if you haven't requested a GPU allocation, then this would fail. And if you've only requested 1, you'd only see 1 here. So it's definitely a useful thing to run in the first time you try to run a job. So I'll move on from talking about the node architecture to talking about programming models in general. So I'm not going to go into this slide, but you're used to building, if we like, traditional CPU-based HPC applications at scale on a platform like ARCHER2. And you have a range of programming models that you can do that with that I'm not really going to describe because it's not really the focus of this. But when we want to go to the GPU, the question is, what are our choices in the programming model that would target the GPU? And quite often we use what's called an offload model, because we offload parts of our computation to the GPU. And that's what I'll think about on the next slide. So there are various approaches to this. One is that we say, we hope that most of our application computation is embedded in libraries. So it might be that we're using BLAS, or we're using a sparse solver. And if we're lucky, there's a GPU library to do that. So the simplest thing we could do is just take our application, use GPU accelerated libraries, necessarily move our data to the GPU. And if we've got enough data and the computation is enough, that might be all we need to do. So that's just the very simplest approach that we can take, which is just to use libraries. Another approach, which is kind of intermediate in complexity, is to use a directive-based approach. So you might be familiar with OpenMP for CPU. So both OpenMP device directives and OpenACC give you a directive-based approach where you mark up a set of loop nests, and you are allowed to, or you can declare that some set of loop nests then should be moved to they should be executed on the GPU, and there's associated data movement that you need to worry about. And then you have programming languages and frameworks at the highest level. So things like Cocos, Raja, HIP, SYCL. These are all things that potentially you can use to target GPUs. Now, some of these are provided within the software stack that's available on the GPU nodes, and some are things you'd have to go away and build, or we could help you to build if we knew you wanted to do that. And there's a trade-off in kind of how high level you're operating, complexity and performance often with the choices you make. So the lowest level thing for most people being something like HIP on an AMD GPU. So kind of that's the big picture. So now we're going to think, okay, so what development environments are actually available on the GPU nodes? So, and I'm thinking of this in two perspectives. So one is that you're used to the Cray programming environment that's available on ARCHER2. And I should have said at the start that I'm assuming you're familiar with ARCHER2. So that's the basis I'm starting from. So you're familiar with that environment, and that environment is also capable of running I mean, it's a multi-vendor, multi-architecture environment, so it can run across AMD and NVIDIA Accelerator. So it had that capability, it's just it wasn't exposed on ARCHER2. So that's one aspect of the program environment. It's a traditional program environment you've seen, but it's perhaps some aspects you've not played with before. And then the other one is that the vendor of the GPUs, in this case AMD, provides a stack. So this is the AMD ROCm stack, and you can just directly use that stack if you wish to. And I'll explain the difference between using those two stacks. And of course, the top one is taking advantage of the bottom one on this slide. So this is just thinking about the scope of the whole programming environment, and you can see that I wanted to highlight that it is a multi-architecture environment. If you remember the Hector service, that was AMD processors. The Archer service was Intel. Back to AMD again. And you've seen probably some large systems in the world that were installed by Cray and had either AMD or NVIDIA processors in them, NVIDIA having the longer history. So here you can see that there's the capabilities you have in this program environment are interfaces to the Cray programming environment, the CCE compiler you're used to, the AMD one. So you might have tried the AOCC compiler on ARCHER2 for CPUs. There's an Intel programming environment. We haven't installed that on ARCHER2. There's an NVIDIA programming environment. There's a GNU programming environment. And then there's the cross-cutting capabilities of that. So you're used to MPI implementation, performance tools, debugging tools that work on all of those environments. Okay, so if we start with the Cray specific one on the compiler side, so this is the default compiler on ARCHER2 today, and that has the traditional features of C and C++ and Fortran compilers, and it had OpenMP, but it also supports GPU compilation and program models that are appropriate for targeting GPUs. So you can use the CCE compiler to do OpenMP device offload and OpenACC for Fortran and HIP compilation, and it interfaces to an MPI that's GPU aware. So that traditional environment you're used to goes across onto the GPUs. From the other environment you're used to, the new thing that you'll see is a ProgEnv environment for the AMD. So these are the GPU. So this is an interface between the rest of the program environment stack and the ROCm AMD compilers. And here's just a slide to outline some of the choices you have and which environments provide those choices or not. So when we talked about libraries, there is something called libsci-ACK, an accelerated version of the libsci library, and I'll say something about that in a couple of slides later. And there are libraries, many more, in the AMD ROCm stack, and I'll explain a little bit about those later. If you want to do OpenMP offload, then you can do that with the CCE compiler for Fortran and C, and you can do it with the AMD compiler for C. OpenACC is only supported by the Cray compiler for Fortran. OpenACC for C is supported by both the Cray and AMD compilers, and HIP is supported by both the Cray CCE and the AMD compilers. And these are the modules that are available. So you're used to the top three. The new one is ProgEnv AMD, which is giving you an AMD LLVM compiler with GPU support. And the drivers are what's listed on the right-hand column here. And now for completeness, I've listed these weird mixed modules at the bottom, just to let you know that there are some mixed modules that enable you to mix different Fortrans with this stack. And there's also a complexity around how you compile applications that use different models that target GPUs, and we're not going to get into that. That's something we might cover in subsequent training. We'll do quite shortly. Not sure when yet. Hopefully within a few weeks to a month. So we'll cover those more details, specifics later. But just to be aware, if you see those modules, that's what they are. And the other thing I just threw in here is just remember, if rather than using a compiler, you're using some environment that uses Python, there is a Cray Python module that's more recent than the system one, and it's integrated with things like NumPy and MPI for Pi. So start with that one rather than the default one. So the next topic is something you should be well familiar with, so that I'm not going to say much about the introductory piece of this, which is those environments work both by using the module context, and which is LMOD on ARCHER2, and using wrappers that essentially are interfacing your compilation with that whole environment. So that's still true. So the question is, what do we need to do to target the GPUs within this module and wrapper environment? So we have to do a few things. We need to start with an overarching programming environment module. So here I've chosen Cray, but I could have chosen ProgEnv AMD. Then to be complete, you should load the CPU module that defines the architecture for the CPU you have on the node you're targeting. So, and you need to be careful about which system you're on and what those differences might be. So on some systems, there's a big difference between the architecture on the node you target and where you compile. And it really matters what you choose here. So on ARCHER2, technically the correct module is to load Cray PE x86 Milan instead of the Cray PE x86 Rome. But to all intents and purposes, I don't think it will make any difference. There's such a small difference between those architectures. I'm not sure the compiler even would do anything different. So, but just for completeness, I'm mentioning that because you might go to some other system where there's a Trento processor or something even newer. So you need to remember that step. I wouldn't necessarily say you have to do it here. But the next important one is the GPU architecture module. So this is analogous to the one that's used to target a CPU. This is targeting the GPU architecture and telling that stack how to build an appropriate application, how to interface with the real compiler to give you the right target. And the gobbledygook, if you like, name for this is Cray PE Accel AMD, so you can understand that. And then GFX90A is the architecture specific to MI200 series processors. So that applies to MI210 and MI250X. And then the last thing you need to load is a ROCm stack module called ROCm. So that gets you the lower level piece of the software stack. So the first one and the last two are things you have to load when you want to use the whole programming environment to target GPUs. And what that's doing is it's injecting some very specific architecture-specific options into the basic compilers that you necessarily probably don't want to know about. So here I've shown you that I've loaded Cray PE Accel AMD GFX90A, and then I've called FTN, and I've added this Cray PE verbose option, which is going to spit out the options that are actually passed to the individual compiler drivers. And you can see there are things like H-Accel, AMD, GCN, GFX90A, the kind of thing you don't want to remember. So it's setting up the compilation with the right options to target the GPU. So you don't need to know about that. And I should just mention, if you're compiling for OpenACC or OpenMP offload, there are man pages that you can look at to see the specifics of how the compiler might deal with those. So that's the first crucial thing. Yeah. Did you have a question, anyone? Okay, so and I'm hoping there's a team of people watching the chat, so I'm hoping I can't see the chat, but in the background, I'm hoping if there are any questions, then people are addressing them. So the last module I mentioned was the ROCm module. So this is the module that's giving you the low-level AMD ROCm stack. So there's one module only currently on ARCHER2, and it's setting up things like your path to give you access to certain commands, like that ROCm SMI one I mentioned. It's setting up LD library path to give you access to the correct components and libraries you need. And then there are other things like profilers that get put in your path when you load that, as well as the drivers for the AMD compilers. So if you want to build an application, so this slide is saying, given some examples I want to build, and these happen to be the examples that we use. If we do training with examples, these will match some of the examples for practical sessions. So I've loaded the relevant modules at the top. So I've loaded the Cray environment, the x86 Milan option, the accelerator option module, and the ROCm one. And then, so the first example here is to build a Fortran application that wants to use OpenAC. So the option there is -HACC, which happens to be the default, so you don't actually need that. The second example is using OpenMP, so the option is just FOpenMP. So that gives me OpenMP device directives. So it's all one thing, OpenMP. So the fact you're using OpenMP means you can use the device directives. For the C or C++ compilers, again, FOpenMP, and to build an application that's using the HIP API. So HIP is, be careful what I say here, HIP is AMD's version of CUDA. So if you know CUDA, you know HIP. You just replace CUDA by HIP, essentially, with some slight differences. So you do cc-x HIP if you want to compile an application to use the HIP API. And one thing I'll mention, because I know it's been confusing for people, in the second example, there are some other things here like -DOMP and -DOMP target GPU. Those are not things you need to put in a generic compilation to use OpenMP with the C++ driver. Those are specific to the stream application that's being compiled there. So you may find that for a particular application you might have to pass some hash define, some definition to it that tells it to do a build with a particular API. That's a possibility. And then, because I'm not going to mention it any elsewhere, if you're doing an offload directive-based model using the Cray compilers, there's an environment variable called cray-ac-debug that you can set, and it will print information on standard output telling you about kernels that are launched and data movement. So it's a useful thing to try. And similarly, if you're used to using the Cray compilers, there is a capability to get a compilation listing to understand how did the compiler map the loops in your source code to the hardware. Did it block the loop? Did it interchange loops? Did it multi-thread them? There are similar things in that output that tell you whether that loop was targeting a GPU. And that applies for C and Fortran. So for AMD's compiler, the same thing. So I've loaded progenv AMD now. That means that those wrappers are now going to use the AMD compiler. So it looks very similar. I can build the stream example with the driver here, and it's just the same thing. I pass the FOpenMP flag, and I can do cc-x HIP to do a HIP compilation as well. So it's pretty much identical. And then there is one thing I just want to mention, which is you can directly use the ROCm compilers, or HIP-CC, which is the low-level ROCm compiler to do HIP compilation. If you do that, you're going to have to pass the architecture flags, the ones that we mentioned a few slides ago. And then the other aspect is if you do that directly, you also need to link with MPI or any other library that you want to use that's part of the Cray programming environment. So the purpose of this slide is to say, okay, let's say I want to use HIP-CC directly without any compilation wrappers. How do I load in something like MPI? So the example on the right is just saying, if you've loaded the progenv environment modules and the Axel module, you'll get some environment variables that will enable you to find those libraries, and you can then inject those libraries into your build. You don't actually need the top two modules to do the compilation, but they're just essentially giving you the environment variable definitions. So you can see on the right side, a lot more complicated because you've taken the raw compiler without any of the integration with the program environment. On the left, you didn't have to say any of that. But you may have an application where this is an appropriate thing to do. Okay, and just another reminder about the different program environments available and what the raw drivers are called and how you can get help output from any of those individual drivers. So if you remember from the existing ARCHER2 environment, you have a difference between the wrapper man page and the man page of the final driver that it calls. So you just need to be aware not the same thing. And because we've now moved to Clang on the C side for the Cray compilers and AMD's all based on Clang, there's a beyond enormous man page that you can enjoy looking at if you want to, and if you do the help option as well. So that's compilation. I hope I covered. The next thing is, I said I'd mention something about the libsci library. So libsci has a version called libsci-ac. This provides, it's basically giving you dense linear algebra. So it's giving you BLAS, LAPACK, and SCALAPACK support. And it was written to be a nice to use, easy interface so that you wouldn't really have to change your code at all. It's compatible with, but independent of OpenAC and OpenMP. And it's essentially providing you a nice wrapper to whatever the vendor GPU libraries would be. Now, one nice thing about this is it has an automatic API which will work whether your pointers to your data are GPU pointers or they're CPU-based pointers. So you can look at intro libsciac, that's the man page for this, and to give you an idea, if you want the automated interface which is shown at the top, this would allow you to call something like DGETRF with data that's either on the accelerator or on the host. So here, H_A means array A is on the host, and D_A means it's on the device. So if you call this library with data that's on the CPU, it's going to get moved to the GPU and back. And if you call it with data that's on the GPU, then the operations will be completely on the GPU. And there are also specific device and CPU interfaces as well that are optional. So that's one nice entry to using some libraries. So to summarize all of that, we have high-level program environment module, so you can use Cray or AMD, the CPU target module, the GPU target module, the ROCm module, and then of course you can load any other modules for other software you have. And the wrappers are hopefully making your life easier. And a lot of these things I'm talking about will be documented, I hope, today. I'm not sure when it went live, documented on the ARCHER2 website. There's been a lot of work going on by people in the CSE team to put that together. So now we're on to some smaller topics at the end. So were there any important questions while I'm at this point, if anyone wants to tell me, that weren't answered?
No, there's a question in the chat, Harvey, but Doug and myself have dealt with it.
Okay, cool. Okay, no problem. So the other thing I just want to make a note about job placement, and this is one of these topics that is important in particular situations. So it's more important if you have a node that has 2 sockets, because if you communicate across those sockets, you're going to see a drop in performance. It's likely to be much less important for the GPU nodes, but there still is some NUMA effect of where the locations of things are. So what I'm trying to say in this slide is that may not be a big deal, and if you're using nodes that you're sharing, that are shareable, and you've asked for 1 or 2 GPUs, the default distribution you've got from the Slurm setup that EPCC did will be fine, right? Don't worry about this. I think it'll be fine. If you've got exclusive access to a node, then my high level advice would be, and if you care about performance, right? If you really want to go for the absolute, what's the fastest way to launch my application on this particular GPU, if that's something you're interested in, associate 8 CPUs with each task. Use a wrapper script to pick one of those GPUs, and in fact, you can choose this GPU based on what Slurm local ID is set to, and then you can check the binding you get to the GPU using a tool that Oak Ridge came up with, which has got a stupid name called Hello Job Step. I mean, they should have renamed it when. So here's an example. Let's say that I want to run. I said 8 MPI tasks per node, but it's only 4, right? So I want to run 4 MPI tasks on a node. I've asked for 1 node. I've asked for 4 GPUs. And there are 2 ways you can request GPUs, actually. So you can say number of GPUs I want, which could be 4, 8, or 16. And there's another syntax that says I want to use so many GPU resources on a node, which would be limited by 4. This is the former one where you've asked for a number of GPUs. I've used an exclusive allocation here. I should have said exclusive as well when I launched this, -- exclusive. Oh, I did do, -- exclusive is in the middle. So I've said, I want SBatch -- exclusive, and I want to use GPU-EXC. I'm only using 1 thread, even though I'm jumping 8 at a time. I've got 4 tasks. I'm using a wrapper script to set Rocker visible devices to the local task number. And that program that was created by Oak Ridge is producing this output, and it's saying MPI task 0 has and its 0th thread is running on hardware thread 0, so like CPU 0. So if I go down that column, I've got CPU 0, 8, 16, and 24. I'm running on the same node. I'm using the 0th virtual seed GPU. I'm using the real GPU 0, 1, 2, and 3 in sequence. And they're in the bus ID is the PCIe location. So it's proving to you you're using different GPUs. And that allocation scheme is the optimal one. You have essentially a node layout where each NUMA node maps to one of these GPUs in sequence. So NUMA node 0 maps to GPU 0 and NUMA node 1 maps to GPU 1. So if you really want to care about the nth degree of performance, look at this, and we'll discuss that a bit more in the longer training we'll do. And then the other aspect of this is, what about the network interfaces? So if you remember that node diagram, we had 4 GPUs and we had 2 network interfaces at the side. Now, it just so happens that they're connected to NUMA nodes 0 and 2. And the MPI library has various policies that it adheres to decide on which NIC your process will have affinity with. And there are environment variables that control this. One of those is mpitch OFI NIC policy that you can set to GPU, and that means that you get the closest GPU. So for the case of running 4 tasks, that makes sense. And there's another environment variable, mpitch OFI NIC verbose, and this will show you in the standard output a table of where all your resources are. So it'll show you where the NUMA domains are, where your CPUs are running, where the GPUs are, and not where the GPUs, where the NICs are. So that's a useful way to check what you've got. And on any new platform, I always think it's good to just run some sanity check jobs just to see that things are like you expect them. But I don't want to over egg this too much. I think we don't really understand what the performance implications are of getting this wrong. We can think of examples where it's probably bad to do certain things, but in general, if you're sharing the node, I wouldn't worry, because you're going to be constrained by Slurm anyway, in a way that makes sense. And if you have exclusive access to the node, then maybe you think about this. So then the other topic is MPI communication, where you want to do the communication from the GPU. So and the MPI library has this capability. So there are 2 choices you can see if you look at the diagrams at the bottom. One is that you have data on the GPU, but you need to communicate it back to the host and then back to the GPU. The other one is that you can directly do a transfer from GPU to GPU. And the GPU library can do the direct transfer, but you have to set some settings to make that happen. So and this is a useful thing to do if you can possibly do this in your application. It's always the case that minimizing data movement is a good thing to do. So and as you can see, we have GPU to GPU connections in the bottom that we can take advantage of. So the way you do this is, actually I should have said as a background, there are a couple of mechanisms that in the hardware that support GPU to GPU communication. One is kind of GPU to NIC RDMA, and the other one's peer-to-peer communication to the GPU. And this is available in the program environments you're going to be using. You need to have loaded the relevant GPU architecture module, and you have to set this environment variable mpitch GPU support enabled to 1 to turn this on. Now, if you turn this on, you're essentially saying that your variables can be GPU variables. So you need to be sure that you've done that, because if not, your application's your application will work. But if you haven't set this and you try to use GPU buffers, then it will crash. It will just get a crash at runtime. And the MPI man page, if you look at MPI_GPU, you'll see a description of this environment variable. So the other thing that I've not said so far is anything about the AMD ROCm stack that's provided it's in the directory ops ROCm, and the ROCm module is giving you access to that. So this is, in some sense, is a self-contained stack, and is also something that we've interfaced to from the programming environment. And it provides a range of things. So it provides the support for the programming models that I mentioned, so OpenMP, HIP, and OpenCL. I've never tried OpenCL, and I don't know if it has, but I think it's supported. It supports frameworks. So AMD in general support frameworks like PyTorch and TensorFlow, and there are versions of those accelerated to use GPUs. It gives you tools. So some of the tools are quite interesting. So there are tools that help you convert CUDA applications to HIP. So one of them is called Hipify, and it exists in both a kind of compiler-centric tool, the Hipify Clang, and as a Perl script. And there is also support for interfacing HIP to Fortran applications, and there's a tool that helps with that. There are the low-level AMD compilers. There are also libraries, and there's a range of libraries here. So with names that don't necessarily tell you what you do. So I think Elution is sparse linear algebra. BLAS, you know, BLAS is dense linear algebra. FFTs or FFTs. Prim, I think, is sorting, scans, that kind of thing. Random numbers. RICL is a low-level communication library. Solver and sparse are other solvers. So there's a range of things. So I would think that if you're doing sparse computation, you might want to look at those, or if you're looking for some solver. And then the other thing is that AMD also have debuggers and profilers. And Douglas is going to say a little bit about that, and very soon, actually. In fact, now.
Hi, can you hear me?
Yes.
Cool. So
Yeah, we're just going to present some slides on what the options are available on these GPU nodes for profiling. So the kind of good news is that for those familiar with CRAPAT, the Cray performance analysis tools that we provide, so there's also capability available in the GPU nodes for this, and this enables to get kind of a whole program analysis of a run on one of these MI210 nodes, where CRAPAT will provide, as well as information on MPI activity, information on activity on the GPUs themselves. For a more low-level approach, you can use some of ROCM's tools, so specifically ROCPROF, to profile individual kernel behavior. So you need to use sampling or tracing. So actually, I was going to go back. Could you go back to the ROCM stack? So I was just going to mention here, for those that are familiar with NVIDIA tools, so ROCPROF is kind of equivalent to, so ROCPROF, OmniPerf, and OmniTrace are kind of on kind of different levels. So ROCPROF is equivalent to NVProf, so quite a low level profiler. OmniTrace is equivalent to NSIGHT, if anyone's familiar with that, kind of a higher level approach. And OmniPerf is equivalent to NSIGHT compute, which is kind of for kernel use on a GPU. So OmniPerf and OmniTrace require a separate local installation, which we won't get details of here. But if you want to know, we can give details for that.
Yeah, and that's why they're coloured, because they're not included within the software distribution that's installed. And I meant to say, actually, I forgot to say when I got to the slide, so if you bear with me, Douglas.
Yeah.
I wrote ROCM open software stack here, and it's a world of difference, I think, from what you might have seen with other vendors, which is that lots of these things, you can just go to a GitHub repository and see the source for them.
Yeah.
Which is kind of very refreshing and unusual. I don't know how you want
pretty much everything. All those libraries, the debugging and profiling tools as well. It's all there. And if there's an issue, you can raise it directly.
So back to you, Douglas.
And it should get fixed. Okay, so specifically for perf tools here. So we're giving just sort of details of the most convenient modules. So usually the things within a workshop, we'd encourage users to try first. So the perf tools Lite module. So within here, there sits a perf tools Lite GPU, and so enabling that will result in output, kind of text-based basic output from the PAT report program, or you can get more detailed information which can be viewed in the Apprentice-2 GUI. So in the next slide, we're just going to go through kind of the basics of what you would do. And if any of you have been to one of our workshops before, you've probably seen a very similar slide. So the basic way to profile your application would do the following. So you firstly load PerfTools Lite GPU module, as well as loading the relevant GPU modules that Harvey had mentioned previously. You do make clean make. You then launch your job on one of the GPU nodes, run successfully, then a directory will be created of the form, whatever, executable plus star, and then there's going to be kind of data within there that can be analyzed further, either using PAT report or Apprentice. There should be text-based output directly to your Slurm job output as well. So an example of this on the next slide. So this is just from the Hymeno benchmark we ran, and it just gives you an idea what to expect. So we're zooming in here on table 3, which gives you data on specific to memory transfers. So we can see here that, as well as kind of MPI specific things, we're getting information about hosted device memory copy here on one of these lines. I can't have a pointer enabled, and we can see a copy from within the actual Jacobi kernel itself. So moving on to ROCPROF. unless you had something to say, Harvey. Okay, so so this is a little bit more low level. So in this case, it's necessary to load the Rocker module. So there's no MPI support. So I would say the most effective way to use this would be to launch it with a wrapper script like the following. So within this wrapper script, here we're calling rockprof. So if you've loaded the Rocker module, then rockprof will be within your path. So you create a directory. We're specifying our output to a CSV file for ease of kind of visualizing the data afterwards. The settings I've got here, so base names on will truncate the full kernel function names, and dash stats will generate a separate kernel execution state CSV file, which kind of gives you a more abbreviated data, and we can just visualize that in the next slide. And then we launch our application in the following way. If you go back, Harvey, to the last slide, with a wrapper, and then single ranks can be profiled separately. I mean, for most applications, it'd be satisfactory to just profile a single rank. But if you are doing more complicated things where different ranks are doing different kinds of compute, then you could write a more elaborate wrapper script to kind of pass this data out into separate CSVs. So if you look on the next slide, Harvey, we just have the visualized output of one of these CSV files. So we have the kernel names, the number of calls to them, the total duration, average, and then a percentage. And then this was within Excel, so we can quickly produce a pie chart showing us where the kind of heaviest usage in terms of the kernels are. And the next slide is just documentation. So the usual way you can get documentation through either the module help, manual pages, specifically help for PerfTools itself, and then web pages, either our performance analysis web page or AMD's web page on rockprof. Of course, there's also the GitHub for rockprof, for example, if you had particular questions for AMD. Okay, so GDB for HPC. So there's also possibility for, as well as profiling for debugging kernels on the GPUs using GDB for HPC, much like one would do on a CPU. So for a more detailed view of this, we would suggest we gave a debugging webinar a while ago, but I think it is available online. So if you were more interested in debugging, it'd be quite useful to view that. We may run this in the future again, perhaps, Harvey, as well as a profiling one.
Well,
yeah. So to go back.
Sorry.
So just the process for using GDB for HPC. So you load GDB for HPC, you load the Rocker module. You would also have to specify here this environment variable for Slurm. So this is required for GDB for HPC to actually detect the GPUs. The next one is not essential, but is useful for the GPU kernels themselves. You then build your application with debugging enabled. You would then request an interactive session. You would then run GDB for HPC, and then you'd use the following launch command, where the only thing that would really differ is this -- GPU to specify that you're using a GPU. And it enables the possibility of using rockGDB. So when you do launch, it should tell you you are able to check. Actually, if you go into GDB mode, you are able to check whether you're using rockGDB or not. So that's one way to check whether you're actually using rockGDB and whether you're able to actually debug kernels on the GPU. So next slide, Harvey, is just an example. So we've got an interactive session. We've launched GDB for HPC. We use this following launch command to run this pip executable. we set a breakpoint. We then continue until it hits a breakpoint, and then we just call info on all the threads, which tells us that we are actually, in this example here, running on the GPU. So very, very simple, but we just wanted to give an idea that these tools are here and they are working kind of as expected. I would say for GDB for HPC, it's fairly reliable, but this is a fairly old software stack, so things may not work, which might work in a future release. Is that fair to say, Harvey?
Yeah.
Yeah, and you can skip the slide. There's not really just final remark.
Okay.
And so the next two slides are just kind of our initial experience from running and compiling a few applications on these MI210s. So firstly, we took a CUDA port of the T-Leaf Mini app, and we ran Hipify Perl on the kernels to produce a HIP version, which worked surprisingly easily, aside from a few kind of NVIDIA specific hardware changes that needed to be made, warp sizes and things like that. So this is a Fortran with HIP code. And then when we ran it, the performance was more or less in line with expectations. As Andy discussed earlier, these are kind of almost equivalent to half an MI250X. So comparing to an internal machine with MI250Xs, we saw kind of a runtime that was double that on an MI250X, so kind of as expected. For CP2K, so this is Fortran with HIP. The compilation was fairly simple. We just took the master version and compiled with the following required flags. And again, when we ran this, the performance was more or less in line with kind of expectations for a particular benchmark. We tried lamps as well. This required a CoCos build, slightly more complicated than CP2K, but it was fairly easy to get up and running. And again, performance was more or less in line with what we'd expect for the MI210s. Next slide. So NAMD, it was a bit more involved. So it required a specific version of NAMD itself and a few modifications to the build process. So this is C++ using HIP, Charm++ in there. But once it was up and running, the performance again is more or less in line with our expectations. And finally, GROMACS. So this required an AMD HIP port that is available on GitHub. Again, there are some available ports on this GitHub ROCm software platform. So it's worth searching that if you're looking for a particular application. This was a smaller benchmark, so performance was surprisingly close, but I think it's just because GROMACS is so well optimized and we perhaps needed a bigger benchmark for running on GPU. But again, kind of in line. So, I mean, it gives an idea that these are running as one would expect, kind of when compared to the MI250Xs. Anything to add, Harvey?
No, and I was just going to say, don't pin us down about those benchmark numbers. And
Yeah,
Douglas
yeah.
was being a bit what's the word? He was being a bit modest because he did all the work. It wasn't us. It was Douglas. So do you want me to? I can finish actually. So
yeah.
So yeah, so I think the main theme here is that we've provided a resource that's essentially compatible with what you're used to on ARCHER2, right? So as we did for KNL on Archer, it's not large, but it's something that people can get started with if GPUs are new. Historically, the community on ARCHER2 has had no interest in GPUs, but the world's going that way, and there's resources to help people with ECSE projects, as mentioned by Andy earlier. And we're doing some activities in the COE as well, engaging with particular communities over the next year. So Hopefully you can take advantage of this. I should say one thing, which is that in order to keep consistency with the existing service and not create any risk by installing newer software, we kept with the same software version that was already on ARCHER2. So it may be that there are newer compilers with better capabilities, particularly for OpenACC. I know that the support's improved dramatically for Fortran for certain applications like Icon. Things like Python profiling. PerfTools can do GPU timelines, but not in the version that you've got. So there's a picture there of what you could do with a newer version, and I think the GDB for HPC would be more robust as well. There are situations where you'll try to stop in a GPU kernel and it won't work. So you can run RockGDB directly, but it's a bit of a learning curve for RockGDB, I think. GDB for HPC has this nice aggregation on top that nicely summarizes things from multiple processes. So that's something we'll look at, which is whether we can bring a newer software version at some point. But there's no concrete plan today, right? But that's something we'll look at. So I don't know, were there any further questions?
Not in the
And
chat.
there was
But...
Andy.
No,
are you still online, Andy?
Yeah. Thanks, Harvey. Thanks.
There was something you said that I wasn't 100% clear on. So,
yeah.
As far as I understand it, the ECSE program is supporting GPU activity, but it wouldn't necessarily have to target these nodes, right? These are really small.
No.
It can target running somewhere else. So
Yeah. So the GPU ECSE core is only focused really on using accelerators, and that's accelerators of any technology. So, for example, it could be NVIDIA technology, even Intel GPU technology. There's no specification that it has to be these AMD GPUs on ARCHER2. Mark's asking if the GPU, if the GPU ECSE was awarded, would they get any preferential time on the queue? That hasn't been discussed. At the moment, the GPU ECSE core, because it's not targeting these GPUs, the reason I mentioned it was because they both contain the acronym GPU, really, rather than any specific link. As far as I understand it, it doesn't have any provision for awarding compute time. So, for example, if you want to test on Intel GPUs, you'd have to have access to a system with Intel GPUs to do your development on. You'd have to bring that with you for the ECSE core. Now, there are academic systems out there with all the various different types of GPUs. The tier 2 systems have and some of the Dirac systems have AMD GPUs. Have the new NVIDIA GPUs. The system down in Cambridge, Dawn, has Intel GPU Max processors, and I think one of the Dirac systems in Durham also has a small number of AMD GPUs, different types. So it's not explicitly linked to the core, but we could consider having as Alan says, having a priority queue for that sort of testing if particular projects needed it. And were awarded through the ECSE call. As I said at the start, the scheduler configuration setup and limits are subject to review. We've gone through what we think is a reasonable first fair way of giving as many people access. But if that doesn't prove to be the optimal way to do things, then it'll be reviewed and changed.
So I think we're open to any questions now.
Yeah,
we left a lot of time in case anyone wanted to do that.
Yeah, so Harvey and Doug and the HP people and as the CSE people and myself will hang around for a bit to answer your questions if people have them either in the chat or you're welcome to speak up too. But if you want to escape and go and do something else, then that's just fine as well. Thank you for coming along and your interest. If you think of any questions, this session has been recorded and will be made available via the ARCHER2 website and YouTube channel in the usual way for these webinars. And if you think of any questions afterwards that you wish you'd asked but didn't manage to ask at the time, then please just send them into the usual ARCHER2 service desk and we'll do our best to answer them there. So Andrew, I don't think we have good enough result. I mean, as Doug said, he he's tried compiling some things and running some simple tests. We don't even know whether benchmarks are the right benchmarks to choose or things like that. These were tests just to make sure that we were getting some sort of reasonable performance on these, that something wasn't fundamentally broken in the architecture somewhere, rather than things to do actual performance tests. I think future real performance tests on these GPUs and then maybe comparing to other models is a future piece of work. I don't think we can say anything.
Yeah, I think
concrete.
am I still? I'm not muted, right? So
no, yeah, I can hear you, Harvey.
Okay, I'm trying to go backwards on the wrong slide. so it's ironic you asked that question actually, because we did have a comparison with an NVIDIA A100 I think on here, but I asked Douglas to remove it because, as a company trying to be agnostic to vendors, I didn't want to put performance numbers that had comparative performance, because then we should have done a much better job. Douglas just did as fast as he could to get some numbers, to get some indicative performance, to basically match what a normal user would do, right? Try to get something built, get it run, although of course we've got some expertise here, but get it running, see what performance we get and do some comparisons. I think if we were going to put comparative results between different vendors, we would have to be much more careful that it was a fair comparison. And we didn't have time to do that. So I thought it wasn't right to do it. So that's why we didn't do that. But hopefully that's something you can do with applications that you know about already on other platforms.
I think typically the experience in the literature that I've seen, at least for most common applications that are sort of a bit more mature, like I guess like MD and things like that, it's been pretty similar between a single, like an A100 and what would be an MI210 or half of an MI250X. It's around that sort of thing. Yeah, that's true, Mark. It's for testing and development, but you should still be able to get good performance out of it, I think, and do at least not on any real scale, obviously, but up to the sort of 2 nodes at least, and then potentially up to 4 if it's something people want to use all 4 GPUs in the future. I'm sure we can find ways to make that accessible at least for specific periods, so people can do that sort of testing. But you're right, it's not large enough to test out at any sort of real large scale.
But I think if you're interested in GPUs, you're familiar with ARCHER2, it's a nice environment to use, and you can obviously aspire to using some large system somewhere else, either elsewhere today or in the UK.
So Johnny, for the NAMD one, an AMD MI250X essentially has twice the number of GPUs as an AMD MI210. Yeah. Right, so for a node of MI250X is essentially a node with 8 GPUs, and a node of AMD MI210 is a node with 4 GPUs. Okay, so that's why you change the number of MPI tasks, because you want 1 MPI process task per GPU, and there are 8 GPUs on the MI250X nodes and 4 on the MI210s.
So essentially, all the examples are utilizing as much compute on the node as possible.
Yeah, because node-to-node comparisons are always a good one to do.
Yeah, 1 MPI per 1 GPU is the standard model for doing these sorts of things.
Yeah, we realized we dropped it. Well, didn't drop it out of a hat, but the reason we compare with MI250X is because that's the standard board that's been sold in other GPUs, Cray systems, Cray EX around Europe. So specifically Lumi, So it's the thing we tend to compare to, and Frontier, of course, right, in the US.
I think somewhere else.
And if you're looking for experience elsewhere, Frontier and Lumi are places to look. They may have been doing similar applications to what you have, and of course we can put you in touch. Well, we can find out about experience elsewhere if it's relevant to a project here.
Okay, I'm not seeing any more questions, and people seem to be heading off, so we'll wrap it up for there. As I said, there'll be, as Harvey said, there'll be future training events going on around these GPUs, and also you can always get help via the service desk. So yeah, thanks to everybody who came along today. Hope you found it useful and or interesting, or one of the two. And we'll hopefully see you at future events as well.